Hi everyone, in this video I would like to talk about a recent project of mine that looks closer at the field of deep metric learning. And before I explain in more detail what this project is all about, I think it makes sense to first try to understand what deep metric learning is all about. And in a nutshell, it's about finding an embedding space in which a predefined distance metric, such as the Euclidean distance or the cosine distance, has some connection to the actual semantic similarity between images. In addition, we want this relation to hold for classes we haven't actually seen during training. And the way one commonly approaches this is by taking a mini batch of network embeddings and applying some ranking constraints on multiple samples in this batch. And this is different to the normal classification-based setup where you treat every sample in the batch independently. You usually evaluate this by looking at recall performance, normalized mutual information, or mean average precision. And people care about doing this because it allows for zero-shot retrieval applications, meaning you can do image retrieval on test classes without actually having to fine-tune the network or retrain the network on these test cases. In addition, representations learned in this kind of way tend to be very well reusable or generalizable. Now, as I hinted before, research in this field focuses mostly on finding good ranking constraints or other orthogonal approaches that try to just generally improve this generalization, but it suffers heavily from what in this case I just refer to as unaddressed factors of variation. So these are changes in the pipeline, in the common training pipeline of these methods, that actually influence the final performance, but that are left well unaddressed. And this means that there's actually little comparability between different proposed methods because they tend to be implemented and evaluated under slightly different setups. In addition, in this field, what was left unaddressed before was that it wasn't clear what the actual best way was to create such a training mini batch, and also what drives generalization in this field. So what makes one method be better than the other one? And so in this project, I, along with my collaborators, we tried to tackle all these points, and based on the insights we gained there, we also proposed a regularization scheme that reliably boosted the performance of different methods. And so first, we looked into the best practices to create such a training mini batch. And in summary, it's just placing two samples of a class into a batch. Now, while this statement seems very simple, there was actually a lot of experimentation behind it. So we looked at label-based samplers, so different kind of ways to put samples of different classes into a batch, and also embedding-based samplers that also leverage embeddings from a memory bank and try to use these embeddings to propose more information-dense mini batches. And applying this on a wide range of methods, what we essentially found is that, yes, there are better ways to do it than just placing two samples per class into a batch. But by far the best trade-off was just to do so. And so, given this way to construct a training batch, we then also looked into factors of variation in the literature, which we essentially boiled down to 5 elements, namely the batch size, the choice of weight decay, the embedding dimension, the architecture, and the way images are pre-processed before they are fed into the network. So for example, slightly higher image sizes or different variations in image augmentation. And what we saw when we tested variance of every factor against a set of very distinct training criteria, what we found was that each of these factors can significantly influence the final performance without actually having changed the underlying training method. It seems quite trivial, but it was never really addressed, so we thought it was very important to give quantitative support for this fact. We then decided that it was time to implement a whole set of methods in this field and try to do a fair comparison. So under a directly comparable setup, compare a whole bunch of methods that have mostly proposed state-of-the-art performance. And what we found across the 3 benchmark datasets was that performance saturates much stronger than indicated in literature, and that the primary driving factor of improved performance seems to be addressing the sampling complexity of these training tuples. So now it makes sense to use this to try to find why still some methods perform better than other methods. We looked into what people tend to attribute to improved generalization. Intra-class distance, meaning how far samples or embeddings from the same class are from each other, or how far classes are apart. We evaluated the generalization performance against these metrics, and for these 2 metrics we did not find a strong connection to actual performance improvement. But what we found had a stronger connections to generalization was the actual embedding space density, so the ratio of these 2 metrics, and the spectral decay, which was just the KL divergence between the distribution of the spectral values and the uniform distribution. So meaning how many different directions of variance I have in my embedding space. For the latter, we thought of a way to specifically address this, if you look back, to reduce this spectral decay to boost the performance. The way we did this was to flip or replace the negative in the triplet with another positive sample. So this would introduce a novel set of features, but also counter the compression to increase the number of directions of variance and thereby decrease the spectral decay. And on the toy dataset, where you have 2 dimensions, we found that this is exactly what happens. So if you look on the left side, you have your training data on a diagonal and your test data either horizontally or vertically aligned. And if you just train it with a normal DML-based loss, you find that during testing, the network has a hard time to separate these test classes. However, if you just, with a certain probability, flip the negative with the positive, it is able to find new features to counter this high level of feature compression, and is actually able to separate all test classes. And this can be seen also in the singular value spectrum, which is much more uniformly distributed, so less compression. And then applied to real-world examples in green, you see that if you look at the corresponding methods, where R just stands for the regularized variant of the baseline method, you see that in doing so we consistently improve baseline methods and also achieve state-of-the-art. And finally, if you, for each of these regularized methods, if you look at the spectral value distribution, you find that this regularization produces a more uniform distribution of spectral values. If you have any more questions, you can look at the full paper, which also provides an introduction to the field of deep metric learning in the supplementary. And code is also public with some follow-up work already out on arXiv.